Okay, good morning, good morning, good morning. So, Mackenzie, would you do the honors, please, of having me stop and switch focus at, did I say 8:04? Because I have our assessments to get back from last week, and I want to make sure that we can take a look at those. And then if we want to keep them through homeroom, we can do that. So what I would like to do, and I just thought I'd be a little colorful. I didn't have enough pink, enough yellow, enough goldenrod. So you got a variety, blue as well. There's some white in there too. So good morning. Thank you. So yesterday, I understand there was an accident, right? That I didn't know that until. Amen.
Yeah. I really tried. I left at like 7:33. I was really trying.
Wait. No, don't say it again. Don't say it again. I'll wake up with sufficient time. Enough said. Okay. So I need to, let's see. Did everyone get? Yeah. Okay. First, of course, your homework over Thanksgiving is to enjoy your time with your friends and families, form wonderful memories, rest up, all that good stuff. So I just wanted to inform us when we get back from Thanksgiving, then we'll dig into Vesper theory. And we'll be able to have plenty of time for practice. So this is the week we get back. We don't need all that. Well, we could take it, but that'll give us sufficient time. So it's very, very likely that we'll have our chapter 8 and 9 exam that Monday and Tuesday, the week after we return. So I just wanted to advise us of that. Okay. So I would like to use some questions to help us clarify what is required of us with Lewis Dot. So could I ask us, given the color copy that you have, can we, let's just answer ourselves the first 4, right on the front here. The first 4, I harvested them from different areas. That's why the numbering is so wonky. Dig in, lean on your neighbor. In fact, do you want to maybe even move to a lab bench? I know some of you really prefer that, or push your desks together. So we'll work, check in with each other. We'll work, check in with each other. We'll work, check in with each other. So a good 20 minutes to start class today, we'll be practicing. Okay, dig in. We'll check in with each other in 4 minutes. That is, yeah, I numbered them all weird. Well, I didn't know. I just, I'll be right with you. I updated the packet a little bit, so but please use anything for that would like, or like have an extra, and then I gave this as a resource too. I'm doing sure they'll have it. Well, I hope it's good.
So that's
Okay. We can call it a barn. Non-polar covalent, polar covalent, or ion. Really represent a share. It's more than okay. So they are all
largest like it's the positive.
So that's where we would have the greatest unequal share. Yeah, and we sometimes call that a dipole. Definitely, and I hope that that's also a good example.
Yeah.
Apparently, so You're
I'm guessing this is just like the electron.
okay, so there's different terms that we just have to be familiar that pretty much are asking the same things. Dipole, two poles. Well, what is that? In a bond, as far as a pole is concerned, do we have a positive and a negative? Or a more positive and a more negative partial charges? So this could say, which of the following is the most ionic? Which of the following is the most polar covalent? Which of the following has the greatest electronegativity difference? All of those, and which is the largest spectral limit? Yeah. And isn't that also a good example? Because I know yesterday we were kind of feeling uncertain about placement on the periodic table and how we make a call. So hopefully that clearly is the choice.
Like it's not like fluorine, that's like the.
Yeah.
That be wide, or did you say like charge?
No. Yeah, definitely. If you have fluorine or oxygen or nitrogen versus another element, that's setting us up to definitely be very unequal and sharing. But then look what the other element is. And look how far arsenic is from versus carbon and nitrogen. Okay, nitrogen's pretty active.
Said that, like the radius or like how far it is. And it's an aspect of difference as fluorine, so then. When our senses is further away. That make it so that we can see some of the parts.
Yes.
So.
So electronegativity, the measure of the pull an atom has for electrons in a bond. So if you can imagine the atoms of your solution and okay, how far away are the electrons that the nucleus is trying to hold? How far are they away and how strong is if that is? So fluorine, 9 protons in layer. Yeah. You're welcome. You're welcome. But it said we're kind of working on some problems. We're going to share the answers, work on some problems. So I said, but yeah. I have your resources that Ms. Hinder gave me right at that corner of the bench and a stool there. Be okay there. Okay, very good, very good. Okay, can I interrupt us, please? So we need to be comfortable with certain terminology that represents the same thing. So this could ask us, which of the following bonds has the greatest electronegativity difference between your elements? Which of the following is the most ionic? Which of the following is the most polar covalent? Dipole moment. Dipole, meaning one side has a greater electron density. Now these are going to be shared electrons, but the fluorine, because it's so electronegative, is going to be way more negative, and as a default, then that'll be the positive. So the greater the difference in these, sometimes you'll never be asked this. You'll never be asked this, but if it's shown to you in a structure, sometimes you'll see an arrow, and if there's a little line through that, that means electron density, and it's pointing toward where we're going to find the electrons more. I don't know why we call them moment. In fact, I do not like that word because when I was a kid, I don't know, adults would say like, I'm having a moment. What does that even mean? Like, What does that mean? And I think if it's a moment, it sounds like, well, then it's gone. Oh, so we just have to be okay with it. And isn't this a great example of kind of, I don't know, we were shaky on what kind of elements are we going to be comparing as far as placement with electronegativity? Okay, are we good that C is the choice? Okay, so we do not have to do all these structures. Whenever we're asked to find one identical to nitrogen triiodide, so what we could do is there a formula that mimics nitrogen in its valence electrons? Well, arsenic. Arsenic has 5 valence, where chlorine has 7, boron has 3, sulfur has 6. And then 3 halogens, 3 halogens. So I know the bonding is going to be the same, just in case. And then we'd have the 3 pairs, and then we have arsenic, and then the 3 pairs. Boron. Boron is an exception in that it is stable with 6 valence. It comes in with 3. That's a weirdo. We're not exactly sure why. It just is. So we're missing the lone pair, and then now that's going to exceed the octet. And then this fluorine no, we're going to be exceeding the octet there as well. Okay, so D all day long. $11. Go ahead, Rishi. How did you know? So I would look for, is there anywhere that's violating octet? We know carbon never, never, never does. Well, look at this guy. Oh my gosh, that takes out B. What about, takes out C. And then, let me tell you, we're hardly going to have carbon that has an unbonded pair. Hardly ever, hardly ever, hardly ever. So if we check, yep. And so all our carbons, 0, 4 valence, minus 1/2, 8, minus 0. So these are 0, 0, 0 as far as formal charges. But this, 4 minus 1/2, 6 minus 2, yee. There, 1. So definitely. Very good, sir. Very good. And first thing I'd look for, okay, are we violating the octet anywhere? Holy smokes, D. And then we haven't given nitrogen enough. There, done. Plus we know the only things that we're going to branch off each other instead of just building on the center would be carbons. So no, 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 no. So this is the only one, the octet. Okay. Questions at all? Okay. The next, they're having us compare O2, O3, and H2O2 as far as length of oxygen-oxygen bond. All right. Diatomic oxygen. Each comes in with 6, each needs 2 more. Does that drive us toward double bond? O3 is ozone. O3 is ozone. So we have oxygen coming in with 6. Another with 6. I'm going to say here. Okay, we have more than one oxygen, so I'm going to balance one oxygen at a time, treating this as my center. So I'm going to double bond with this on my right And then my oxygen on the right has the octet. But so does this. Oxygen never, ever exceeds the octet rule. So, coordinate covalent bonding. Remember, it does not matter. If you drew yours vertically, okay, this is what we ended class with yesterday. I chose to put the double bond on the oxygen to the right of the center in my first drawing. But what makes that one have the advantage? Because a double bond is a lower energy bond and a shorter bond. Maybe, Bryce, you drew yours there and then the single bond there. If there is a possibility of a different structure based upon the choice you made, right? So, double bond here, single bond, or double bond, single bond. Now, how do we know that that could happen? Often the wording will tell you, careful of resonance, watch for resonance. We didn't get that here. It most often occurs when we have oxygen or nitrogen bound to our center. Excellent. Okay, very good, very good. I'll make sure Mrs. Kendrick gets it. You're welcome. So this will resonate. So we have double bond, then we have this or that. And then they're obviously telling us that the oxygens are going to be bonded to each other. Yeah. We know hydrogens can only single bond. So there's one of our oxygens. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Well, each oxygen this way already has 7. So okay, so we are looking at this bond versus this versus here. Increasing bond length. Okay, which is shortest? Go. Okay. Are you sure? Why? Very good. So, single is longest. Single is longest. Double, triple. So what about this? So, perfect. If a double is there and a single is this, okay, then this double bond is alternating between 2 bonded oxygens, between 2. So it's as if this additional pair is kind of making this halfway. So it's like a single and a half bond. So it's going to be a little shorter, just a little. So this would be the resonating one. Not as short as a true double, not as long as a single. So excellent, sir. Excellent. Laffy Taffy or no? Laffy Taffy or Smarty, sir? Or Airhead? That is a tube. Very good. Thank you. Good catch. Good catch. Okay. Good thinking. Question 15. Go ahead. Okay, do we want to start talking? Okay, so we know hydrogen and halogens can only create single bonds. We just talked about O2. And then yesterday you did N2. So single, double, triple. Now, this x-axis, if you will, is the distance between the nuclei. Here, bond energy. So to break whatever Z2 is, okay, that's going to be there. Yeah, to break X2, okay, and let's look about, this is a little deeper, a little lower. So this would have a little more bond energy. And then this, ooh, the greatest, which will require the most energy to break. Go. Right? The N2. So there's our triple bond. Okay. So I would decide that absolutely by bond energy, by depth. So then next, these are pretty close. I'm looking at now size. Oh, poor hydrogen, so tiny. Yeah. Oxygen, not that much larger, but larger. And double bonded, so they're a little closer, but still much larger. So I think we can clearly say this is O2, and then this would be our H2. Yeah. And so, oh, there we go. Choice A. Yeah. Questions at all? All right. So can I ask you in your teams, go ahead and answer 2A through E.
I got one.
Pretty sure mine sounds right, but I wanted today.
I guess take a little bit. 1, 2, 3, 4, 5, 6.
Like,
I don't really got the dimensions.
yeah, so since it's line, I think we need one. You're just.
Okay, so 2A. Man, I love when, okay, hydrogen's an exception, but we know it's just going to single bond. Oxygen, nitrogen never exceed the octet. So we are just placing our electrons, and I know it's going to single bond there. So when I created this, okay, single bond, okay, there's the one electron from hydrogen, okay, one for oxygen, and then I have another 2, 3, 4, 5, 6 for oxygen. Yeah. Well, if it forms a single bond with that nitrogen, then it has its octet. So sometimes, you can still, or that's the way I do it, still think about each one and how many valence electrons it brings in, respecting the octet for the oxygen, nitrogen, oxygen. Now, this is the only drawing that it can be. You could put the lone pair though here, or a lone pair there. But we wouldn't have the double bond there. Okay, so do not be thrown off by like, oh, I don't know what eco meter is. Do not worry. They're just giving you two values, one larger, one smaller. We know double bond is going to be shorter. So that's the 120. That's the 146. You know, a letter before M, that is some version of meter. Okay. Now here, we need to make sure that for this structure, we are adding. Yes, I know. I already cleared it up with Mackenzie. She did not drop the ball. Thank you, sir. Did you think she did? She didn't. So it was Isaac that was being so rude. No, I asked Mackenzie because I said we're going to go over these and then we'll get it. Yeah, well, thank you, because I just love to talk about chemistry. Okay, so are we good there? Now, you could though have put the double bond there and then the single bond. Okay, could have put the double bond and a single bond, but then this will just have 2 pairs and that will have 3 pairs. But then it says that these bonds are the same length. Resonance. And so we would address that the double bond is alternating between the oxygens such that it's equally distributed. And so the bond length will be shorter than single, but longer than if it were a true double bond. Because the double bond is alternating between 2 oxygens. Okay. I gave you these in angstroms and I forgot. I'm so sorry. I didn't change this. So I think we would guesstimate that here it would be kind of in between. So if you have something anywhere around 1.30 angstroms, that would be 130 picometers. But okay. So just to preview what we will come back to. Oh, how about we'll warm up next Tuesday? Normal charges. Okay. So